Our star somehow found itself the punchline of cheesy science fiction. Dramatic doomsday events like the ones in Knowing in 2012 are indeed fabrications of Hollywood sensationalism, but there's nothing fictional about the potential for the sun to change our way of life. This wasn't so true when there were 13 colonies, or when Babylon was Sumer, or when we lived in caves, but it's true now. We have partly brought that on ourselves. Could you imagine if there was suddenly no electricity? Suburban and rural residents would see the auroras well before the lights go out, but city living would leave you to watch the heavens warning as consolation in the wake of disaster. No water from the tap, no phone. Within 48 hours, no gasoline, no food at the store, no end in sight for weeks, months, or longer. The last time something like this happened was 1859, the Carrington event, at the dawn of our electric age. A massive solar storm set fire to telegraph offices and shocked operators. There wasn't much else to destroy. Smaller bursts of damaged satellites have taken out electricity in Canada and Sweden in the last few decades. We haven't seen the big one again, not yet. Mega flares have lit the skies many times throughout human history and posed no direct threat to us. But now, unlike the past, humans are uniquely vulnerable to a mega flare because of our dependence on electricity. The more dependent we become, the more vulnerability we face. Some experts say destruction could top $2 trillion, others say more. And some say there is a 10% chance of seeing such a blast in our lifetime. There are tens of thousands of us watching every moment of the sun. After this video you will know why, and if you so choose, you will be able to do it too. Why do we watch the sun? because the mega flare is an unlikely yet ever-present possibility. Before learning more about our star, we need to understand just how it interacts with our planet. Our planet came with a built-in invisible defense against energy from the Sun and the galaxy. Our planet forms a complex magnetic field around itself. It is our protective interface with energy from space, our shield, known as the magnetosphere. And this is no conspiracy. The magnetic field is fading. Many sources, including the World Center for Geomagnetism in Kyoto, Japan, have simple visualizations of our magnetosphere. This one shows it weakening over the last 400 years. As of just a few years ago, the field had decreased 10% since the 19th century, and it's hastening its shift. This makes Earth more vulnerable to megaflares from the Sun and galactic radiation. There is no evidence to suggest that the field would ever disappear completely, and evidence does suggest that humans have endured such events many times in the past. However, with our electric way of life, one cannot help but ask the question, how much weakening before the Sun could easily take out our power? These megaflares happen anywhere from 100 to a few hundred years apart, so 154 years after the Carrington event, that aforementioned 10% chance of seeing one in your lifetime comes into perspective, along with just how lucky we've been in our electric age, and just how important it is that we watch the Sun. The primary thing that affects Earth's magnetic field is the solar wind, a force made of plasma and charged particles constantly leaving the Sun. You will notice the flat surface with dark spots is not visible here. The detector is looking for certain ions in the solar atmosphere, known as the corona, and registers back only those, as color. You can also see these large filaments hovering above the solar surface. These are made of plasma, and as we will see later, can be very volatile. Together, these help demonstrate our first important heliophysics principle. The Sun is strongly magnetic. That magnetism of the Sun sustains the altitude of the particles and plasma filaments in the solar atmosphere and often packs those particles into magnificent loops. In addition to tremendous gravity pulling in, there is constant outward force from the Sun affecting charged particles of matter. The Sun is so magnetic that it forces some of those ions out away from it at incredible speeds. This is the first of many graphics you will see here, and a hyperlink to each will be given so that you can be empowered to watch these things yourself. This is the solar wind metrics at Earth as detected by the ACE satellite. Basic solar wind monitoring focuses on density and speed of the solar wind, orange and yellow respectively. With dynamic scaling on the left, it changes to fit the data. Now, on an average day, the ACE telemetry measures proton density of the solar wind between 0.5 and 5 protons per cubic centimeter, usually arriving between 300 to 350 kilometers per second. Now, despite these averages, we often see intense solar wind streams at more than twice the speed and 10 to 20 times the proton density or more. The blast that could take out our electricity could look like this. It's not just protons exiting the solar atmosphere. NASA JPL Genesis mission has shown that about 0.1% of the solar wind is made up of ions of heavier elements, including carbon, nitrogen, oxygen, iron, indeed almost every other known element. Let's take a closer look at those loops we saw earlier. If you will remember, these are strong condensed particle streams in magnetic fields that naturally capture those particles with positive and negative charge. The interior magnetic fields of the Sun often poke through the solar surface and out into the upper corona. The area where these emerge are where you're likely to find sunspots. These areas pop up and decay, can be much larger than Earth, and constantly morph around. The dark area inside is called the sunspot umbra. This is where the actual electromagnetic currents carrying the plasma and charged particles enter and exit the Sun. The orange area surrounding the umbra is the penumbra, consisting of electrical currents perpendicular to the in-out magnetic force of the field creating the sunspot, the same in-out force that makes those magnificent loops. You are looking at an SDO-HMI intensity gram, but for the purposes of watching our solar activity, it is necessary to monitor the magnetogram. The magnetogram shows the magnetic strength of those aforementioned in and outward forces that make the loops. Blue is positive charge, red is negative charge. Now consider how these sunspots morph around, and the fact that many of these are bigger than Earth, and just how powerful of magnetic forces we are dealing with. When the sunspots morph around, those bright magnetic loops entangle, opposing forces often interact, and the particles can be accelerated to near the speed of light. These are solar flares, and they produce large flashes of X-ray radiation that arrive at the speed of light. These are the first sign that an intensified solar wind stream might be on its way. The GOES X-ray monitor is the best way to determine the strength of that radiation. The scale for solar flares, from weakest to strongest, goes A, B, C, M, and X. The largest eruptions, M and X class solar flares, produce enough energy to expel those particles in plasma that were hovering above the solar surface. We discussed that solar magnetism holding them up. That outward push is intensified by the energetic blast of the solar flare, and the particles are sent into space. These explosions are known as coronal mass ejections. As you might have guessed from the name, a coronal mass ejection, or CME, is comprised of much of the same material as the solar wind mass, just more of it. This video opened by portraying an unlikely but real and relevant risk of a massive solar burst that changes our way of life. These CMEs are that very same force. When you see a larger flare, a CME is often visible leaving the surface. Those filaments we discussed earlier also erupt as CMEs, often without a preceding solar flare, which is why large filaments need to be monitored. After determining that a CME has indeed left the Sun, we must next determine if the eruption is headed our way in what's called an Earth-directed CME. Often this footage from the SDO satellite is enough to allow us to make a pretty good guess about what's coming at Earth, but to be sure, we need to check NASA's other satellites. The stereo satellites are usually the first to update, so if you catch our star flaring in the act, head there first. The stereo spacecraft A and B are orbiting the Sun on nearly the same orbit as Earth, but each is a few months of orbit around the circle. Combining with Earth orbiting satellites, they give us a 360-degree look at the Sun. Using what are known as the Core 2 camera images, we get a side view of the eruptions leaving the Sun in Earth's direction. As the stereo A Core 2 looks at the Sun, Earth is off to the left, and the stereo B Core 2 has Earth out of the frame to the right. These can be a good complement to the SDO footage to confirm that a CME was indeed produced, but to be sure it's coming at Earth, we have to go to SOHO, which looks directly from the Earth's orbit. CMEs look beautiful leaving the Sun in the SOHO LASCO images. A disk blocks the glare of the Sun, allowing us to see the particles. When a blast is coming right at Earth, it will look like this. We call it a halo eruption. If you have confirmed an Earth-facing solar flare, resulting CME and the stereo images indicate it is headed in our general direction. A visible halo on SOHO indicates a near certain impact to Earth. Once we have made certain that the potential for an Earth impact exists, it can be helpful to look at one of the Enlil spirals, attempt to model the CME's movement through space. This is NASA's density Enlil spiral. The Sun is in the center. You can see Earth on the right as that little dot. You can see a number of other celestial objects and satellites. This is also helpful to demonstrate that there is natural variation in the solar wind. The CMEs are quite evident on the Enlil spiral when they occur. This is NASA's interpretation of all the data about the flare in CME and indicates whether they believe it is going to impact Earth and when. If you look on the far right, this tilts the frame 90 degrees, places us in the midnight position from Earth ground's perspective, directly opposite the Sun, looking at the CME impact from behind, if you will. The splash will indicate whether the Earth will be hit. NOAA's version of the Enlil spiral replaces that right panel with a timeline graph. They put solar wind density and speed on the same page. They show the timing NOAA believes impact will occur. On the bottom, speed is especially important because we are fairly certain it would take a CME traveling in excess of 1,000 kilometers per second at Earth impact to cause damage to satellites or power grids. We come back to the solar wind telemetry from ACE. When the CME arrives at Earth, the speed and density, yellow and orange, become your bread and butter. They will begin to rise sharply. Medium energy impacts elevate the solar wind speed slightly, like here, with proton densities of 10 to 20 protons per cubic centimeter. Larger impacts we have seen in the last few years pushed speeds to 700 kilometers per second or higher. The big one you worry about would be moving much faster when it hit Earth and probably have a density of 50 to 100 or more. Now we come back to the magnetic shield of Earth, the magnetosphere, and while it is fading, the shield is still strong enough to protect our planet from CME impacts. On the magnetometer, which measures the disturbance in our magnetic shield, calm conditions appear as a relatively flat line, although it is rarely ever completely flat due to natural variation in the solar wind. When impact occurs, the magnetometers across the planet will begin to fluctuate. This is very intuitive. The larger the deviation from the baseline, the larger the disturbance to the magnetosphere. These disturbances can have awe-inspiring and often dangerous effects, as you've seen. This is the induction magnetometer. It measures the frequency of electromagnetically induced fluctuations at ground level, caused by strong solar wind interacting with our magnetosphere, and it shows strong action during significant space weather. The rheometers allow us to see when a weaker shield allows solar plasma to penetrate our magnetic shield and be absorbed in the ionosphere, as indicated by red absorption lines spiking above the blue curve. You don't see much here. This is a day with quiet space weather. This is the rheometer from that April 16th geomagnetic storm we just analyzed, CME to magnetic disturbance, which was a very low-level event. Now this is from a moderate geomagnetic storm, but shows heavy penetration. We often see ionospheric absorption of solar radiation at rates much higher than the geomagnetic disturbance would warrant, and although the subject of some controversy, some observers believe this is a sign of that weakening in our magnetic shield. If you wish to stick with the solar wind telemetry from ACE for your geomagnetic readings, you can get basic data about the disturbances in the magnetic field at the top line, the red and white. Now, without getting too technical, during strong disturbances, the red line will dip very low below the dotted line. We say the BZ component of the magnetic field has tipped south. The further down it goes, the worse the disturbance. The dynamic scaling on the left is important here as well because a large downward spike like this, close to -40, might easily be confused with smaller ones like this, as the scaling on the left has changed to fit the data, just like the solar wind speed and density. The KP index is the best known chart that shows the strength of magnetic storms. Simply put, a combination of factors equate to a simple scale where quiet conditions range in green from 0 to 3. A KP of 4 shows as yellow and, as you might guess, indicates that energetic disturbances are beginning in the Earth system. 5 and above is geomagnetic storm conditions. At this level, You can bet that the auroras are putting on a dazzling light show at high latitude on the night side of the planet. The mechanism by which the chaos begins on the ground is induction. The stronger the geomagnetic storm, the stronger the auroras. In a storm that would cause damage, the auroras would become incredibly bright, extend southward to lower latitudes, and perhaps even be visible in broad daylight. The beautiful display consists of charged particles interacting with our atmosphere in a maintained current known as the auroral electrojet. Now, to put it simply, electric currents induce magnetic fields and vice versa. The energy associated with CME impact from the mega solar flare would cause surges and strong variation over large areas in otherwise weak and consistent ground currents. This could overcharge and destroy electrical grids, leaving the foundational infrastructure of our way of life at square one. Let's review by using the hypothetical mega solar flare. Our job begins well before the flare occurs at the SDO website, the Solar Dynamics Observatory. A link to this website along with everything else you are seeing will be posted for you in one location. Make it easy. This is indeed where you find all those colorful sun images, but our job begins with a little game of sunspot hunting. As you might have noticed, the sun spins left to right as we look at it from Earth, so if we want to catch these things as soon as possible, we look to the left side, known as the eastern limb. We're kind of turned around from where we would look at an Earth map from above, so east is left, west is right. You will remember the magnetogram and intensitygram as the two images that allow us to see and analyze sunspots. You can click the image or one of the links beneath to pull up images or videos. You can usually catch sunspots creeping into view long before they face Earth directly, although magnetic details are usually more difficult to distinguish at this early point. If you want to create a custom video like this, there are two easy ways. At the top of the SDO page, under Data, you can browse the AIA and HMI data, which are the devices that give us those pretty sun images. You can specify your date, time, as well as whichever view you want, even with their colors labeled for you. Some of the composite views are known to be especially captivating. Our other favorite way to watch the sun is helioviewer.org. You can also choose your date and time, even a number of satellites besides the SDO. You can still pick whatever view you want, but you can also add them together and create your own composites, fine-tuning the enhancements if you like. And perhaps the best part of this is the ability to zoom. The movie tab up top will allow you to make your selection. Back to the sunspots. Remember, the larger they are, the more powerful they are, and when it comes to flares, you need positive blue and negative red mixing, not just on the surface, but within active spots themselves. As we look at a large and complex structure to this active region, you can clearly see plenty of magnetic mixing to the sunspot group, but the only real mixing of oppositely polarized sunspots is at the southern edge of the region, and back on the intensitygram you can see those are not as well developed as the bigger ones. By contrast, this meager group of sunspots has its two largest in the middle, very close together and with opposite polarity. This little guy represents potential for M or even small X-class flares, but probably not the big one. If you have a large and magnetically complex sunspot group, you can be sure the potential exists for larger flares, and the closer it is to dead center of the Earth-facing half of the sun, the more directly eruptions would approach the Earth. Included in the list of sources will be the GOES X-ray monitor, one of the most important charts. The mega flare would approach the top if not exceed the frame of the graph. This is where we immediately go to the SDO images trying to find the source of the flare and determine if there has been a CME. Remember, if there's a large filament eruption there will be no preceding flare, instead one may follow as the magnetic fields regain form and begin to surge charged particles near the speed of light, creating the post-CME hider flare. We will use the eruption from the Sweden blackout of 2003 as an example for the Soho Lascaux images. If you have seen a big flare in CME from an Earth-facing sunspot, it would almost certainly be a halo eruption on Soho images. You can see it's brighter at the bottom, meaning much mist to the south. Imagine how bad the Sweden blackout could have been. On the Enlil spiral, the CME would be unmistakable and headed showing clear impact to the little yellow dot, that's Earth, on all three panels. The mega CME would look black and be going very fast. As previously stated, it would likely be going over 1,000 kilometers per second. Solar wind metrics could look like this. And regardless of how you view the CME's impact on Earth's magnetosphere, be it at the top of that ACE chart or on the magnetometers, the readings would be huge. I've actually extended the scaling on the flux gate here because the default scaling would have it look like this. The KP index only goes up to 9, and the mega CME would certainly cause exactly that. The disturbance in the magnetic field coupled with the energized auroral electrojet would induce strong surges in ground currents, potentially destroying transformers, and, if big enough, could combine with our failing magnetic shield to set buildings on fire just like they did telegraph offices in 1859, back when our protective shield was 10% stronger. There are other significant solar events that are important to monitor and understand. Coronal holes are vital to understanding variation in the solar wind, but in order to understand coronal holes we must first look at the umbral magnetic field. These magnetic loops you saw earlier are umbral magnetic fields, but larger fields extend much beyond the confined loops we saw earlier. There are even larger magnetic fields on top of those. The areas that lack fields atop the surface often appear dark on certain SDO views. They look for particles in the upper corona and can't find them, registering black, just like the outside of the Sun image where it also sees no particles. But why are there no particles where there are no magnetic fields? That constant outward magnetic force of the Sun that pushes the solar wind appears to be restrained by the umbral magnetic fields because the solar wind streams from these coronal holes are much faster than normal. This suggests that the particles in the corona, or lack thereof here, which causes the SDO to read black, is due to them all being pushed out by that force where there are fewer magnetic fields to capture and restrain them. The intense solar wind streams from coronal holes can also cause geomagnetic storms. Those particles not only travel at speeds much faster than average solar wind, but they catch up to slower particles ahead of it, creating an initial shock wave to the impact that inevitably causes many of the magnetic disturbances registered at our planet. There is a rare solar event that can actually be directly harmful to humans. While the loss of electricity from a CME could cause a global disaster, a solar radiation storm poses a direct threat to humans in space stations, high-latitude flights, and in severe events, potentially even to those at high latitude on the ground. Sometimes charged particles are accelerated to near the speed of light and arrive much faster than their slower counterpart, the CME. We have minor particle events periodically, but just as we never want to see a huge CME headed our way, we do not want to see a huge radiation storm either. The primary method for monitoring these events is currently the proton detectors aboard the GOES satellite. The dotted line marks the official lowest storm event, level 1. This is the solar particle event associated with the 2003 Sweden blackout. The southern aspect of this storm was so strong that South Africa experienced transformer damage as well. The mechanism by which these particles are accelerated is not fully understood, but it is hypothesized that a magnetic connection between the Earth's magnetosphere and the Sun does play a role. It was 2008 when NASA began describing these magnetic portals. This topic in general is for advanced viewers, but think of the connection acting like a wire between the electromagnetic bodies, the Earth and Sun. And if that portal is surged by a flare or coronal mass ejection, then it is possible that this electromagnetic connection between Earth and Sun might allow the particles to be accelerated to the Earth so quickly. The Earth footprint is the name given to the location where Earth's magnetic field connects to the Sun's. It is shown here so you can watch for eruptions nearby, and you can find this via a free internet application known as the Integrated Space Weather Analysis System. Now, the Integrated Space Weather Analysis System, or as it's commonly called, ISWA, is another terrific all-in-one resource. This free application acts as a portal to nearly all data made available to us from satellites, ground observations, and different compiled indices. The tabs above the panels segment the data so it's easier to find. There are some general things it helps to know about the Sun. It has a fairly constant cycle of activity when it comes to flaring. Activity peaks approximately every 11 years, and right now, in mid-2013, we are expected to be approaching the peak of activity. The cycle has been pretty reliable throughout modern history. It is interesting to note that the Carrington event in 1859 was not during a very strong cycle. Indeed, the fifth largest flare we have ever recorded was during the last low point in activity, known as a solar minimum. These larger events can indeed happen at any time. A deeper look at recent solar minimum reveals the Sun went deeper and endured longer than we expected. And, so far, we appear to be in a relatively weak cycle now. These and other patterns are tracked daily at the Suspicious Observers YouTube channel, where tens of thousands meet to take a few moments out of their day to catch up on 24 hours of awareness regarding our planet, our star, and our interaction. At some point during this presentation, you probably wondered what you would do in a situation like a megaflare. But might I suggest that it is what you do before the megaflare that might determine your fate. Much like you would prepare for an earthquake, you would need food, water, batteries, medical supplies. But due to the long-term nature of such a megaflare blackout, one would probably need more than the standard 3 days worth. Now, you can get supplies in any number of places. Getting a hand crank generator takes a bit more searching. Diesel and gas generators will run out of fuel, and they make fumes and often are loud and attract attention. Solar power is a terrific alternative, assuming you have the money and expertise to pull it off. Most do not. But when you see what the military, police, firefighters, and other professional groups are buying to prepare for what could happen, you have to ask why. Powered by the human body, at high efficiency, portable anywhere, and friendly to the environment. All these images are the property of Presto Wind, makers of this crankawatt energy device. They happen to be watchers of our daily tracking of the solar terrestrial condition, and they wanted to give a gift to their fellow observers by offering a discount on this crankawatt energy device. I have one at my home. I am not a paid endorser. I hold no interest in the enterprise. This mention is wholly merit-based. I invite you to really take in what history has to teach us about how lucky we have been to see several decades without such a megaflare. It takes almost no time to stay informed about the Sun. And for those busiest among you, I invite you to join us daily at this channel for 3 to 4 minutes of complete updates on the most relevant information. Earth's magnetic shield is holding, for now. So is the Sun. Remember, information is the antidote to fear. Be safe, everyone.